Hi, and welcome to our fourth and final video in the Unit 9 Remediation series, where we're going to be looking at reversible changes and the idea of dynamic equilibrium. We'll be picking apart how reactants and products are interconverted and factors that affect whether the forward reaction or the reverse reaction is favored. So Le Chatelier's principle and the idea of shifting left or shifting right. To start, I want to look at this particular equation we looked at in the Part 3 video. As it turns out, this equation is reversible, which means it can run in both the forward and reverse directions. When I say forward reaction, what I mean is converting our reactants completely into products. So taking our carbon monoxide, adding it together with oxygen, and changing it into CO2 and producing heat. Remember, these are all gases, which will be important when we talk about pressure later on. The reverse reaction is, instead of changing reactants into products, converting our products back into the starting materials, our original reactants. So for this equation, it's going to look something like 2CO2 gas changing into carbon monoxide gas and oxygen gas. And the one thing I left off of this reverse reaction is the fact that it requires heat. Because remember, heat is kind of like, in this case, a reactant for this diagram, for this reaction to take place. So in a state of chemical equilibrium, what that really means is that this reaction and this reaction are taking place at exactly the same rate. As fast as this reaction is producing carbon dioxide, it's consuming it and turning it back into reactant particles. What that means from our perspective is that we see no real change when we look at the tube or beaker that this reaction is taking place in. We don't see a change in the concentration of CO2 because as soon as we produce new stuff, it's getting used up. So we see no change in the concentration of either the reactants or the products. And that's the key giveaway that you're in a state of dynamic equilibrium. In order for that to be true, we've got to have consistency in other places as well. If I change the temperature of a system, then it's going to affect the rate of reaction by affecting the number of collisions. The same goes for pressure. If I increase or decrease pressure, I'm going to change how frequently particles collide and therefore the rate of a particular reaction. So those two things will be constant if we're in a state of dynamic equilibrium. What I'd like to look at is these factors that affect if we're favoring one reaction over another. So disrupting that state where all things are equal. And there are three things that can cause those types of disruptions. And the first one is changing the concentration. So change in concentration can disrupt chemical equilibrium. If I increase the amount of, let's say, oxygen that's introduced to this system, so increase my concentration of O2, what I find is that that adds more reactants for the forward reaction to take place. So what you guys know is when I add stuff, it's going to try and use it up to produce more products. So this is going to equal a shift right towards producing more products, therefore favoring the forward reaction. But let's think on a particle level what a shift right means. A shift right means I use up CO and O2 to make CO2. So what that tells me is when I shift right, I'm actually going to decrease the concentration of my reactants a little bit in order to increase the concentration of my product. So when I add an extra O2, the reaction is going to try its hardest to decrease its concentration again by reacting with carbon monoxide and increasing the amount of product that's around. If we look at sort of the opposite and I decrease the amount of O2, you guys know that this reaction is going to try and shift to refill that missing oxygen because I've taken away a reactant that I needed for the forward reaction, thereby favoring the reverse reaction. That reverse reaction is going to try and produce more O2, so this shift left means that I'm going to use up CO2 in order to make more O2 and more carbon monoxide. So I'll see a decrease in the amount of CO2 and an increase in the amount of O2 and carbon monoxide. A different change that I could make to this system comes in the form of changing temperature. So if I change temperature, I'm going to affect the rate of either the forward or the reverse reaction, favoring one over the other and disrupting my state of chemical equilibrium. For this particular reaction, if I increase the temperature, that's kind of like increasing the concentration of heat. So if we look at our forward and reverse reactions, what I see is that heat is over here on the product side. So if I increase the amount of heat that I have around, that's going to help this reverse reaction take place. So it's going to try and use up that extra heat to shift the equilibrium over to a different position. So here, an increase in heat is going to shift this reaction to the left. And remember, a shift left means that I'm using up products to make more reactants. So I use up CO2 and that extra heat in order to make more O2 and CO. So my concentration of CO2 will go down and my concentration of O2 and CO will go up in order to get back to a state of equilibrium. The opposite is true if I decrease the temperature. That's kind of the same thing as decreasing the concentration of heat. So this reaction is going to try and replenish or refill that heat in order to get back to equilibrium. Taking that heat away makes the reactants want to make more products and produce more heat. So I see a shift to the right. And remember, a shift to the right means we're crashing these two particles together in order to produce more heat. So I use up O2 and CO to make CO2. So I see a decrease in the concentration of O2 and CO and an increase in the concentration of CO2. The third change I could make to affect the equilibrium of this system is a change in pressure. A change in pressure affects reactions that involve gases because gases can contract or expand when pressure is changed. So here in this particular reaction, I see gas particles on both the reactant side and the product side. And looking more closely, what I see is that there are 2 moles of gas that are products and 2 plus 1 moles of gas that are reactants. So I've got a total of 3 moles of gas on the left and 2 moles of gas on the right. So in terms of pressure, these reactants exert more pressure on the sides of the container that this reaction is taking place in than do the products. So if I happen to increase the pressure, the system is going to respond by trying to decrease the pressure. And in order to do that, it will move from the side with more gas to less gas, a shift right. And remember, a shift right is going to use up CO and O2 to make CO2. So we see the corresponding changes in concentration. Alternately, if I decrease the pressure, in order to get back to an equilibrium state, this reaction wants to try and boost that pressure up again. So just like the toothpaste sucking up the extra stuff, it's going to move from a low number of moles of gas to a high number of moles of gas in order to try to restore some of the lost pressure. So a shift left. And remember, that means we're going to use up CO2 in order to make CO and O2. So go back, review those 3 changes, see if you can predict how concentrations would change as a result of changes in concentration, temperature, and pressure.